Hi there. So our last video we introduced polar coordinates. We looked at some of the conversions and looked how to set up an integral in polar coordinates. And now we're going to go ahead and go through an example. In the next video we'll talk about how to evaluate this integral, but here we're just kind of setting up the integral. So here's the problem statement we're working with here. Evaluate this integral of xy dA, where d is the disk with center at the origin and radius of 3. So first thing you may want to do is go ahead and plot this out. Maybe use calcplot 3D, but this one's pretty simple, and I think we can look at this without really having to do anything too fancy. It's pretty basic problem. So d is the disk with center at the origin and radius 3. Okay, so essentially we have this circle, x squared plus y squared equals 9, and d is the region within that circle. So let's go ahead and plot this out in our standard Cartesian coordinates. Going to look something like this. And of course our region D is going to be that region inside of this circle here. Maybe shade that. So the way we typically set up this integral would be with a formula such as this down here. And if we're going to do this in Cartesian coordinates, we know that dA is just going to be our dy dx or dx dy. So let's go ahead and expand this integral a little bit so we can fill this in. So we got dy dx here for our dA, and now we got to go ahead and plug in our f of xy. Well, that's already given to us up here, xy, so that's pretty simple. So we go ahead and plug that in. What gets a little more complicated is looking at these limits now for the region, particularly this first one, because we're going to integrate with respect to y first. So that means this is going to be a type 1. So we're going to start here and we're going to go up. It's type 1. So for our lower boundary, we're looking at an equation for this curve down here on the bottom. And since this is, we got an equation up here, and we can sort of solve for y. So we know that y is going to be equal to, on the bottom, negative the square root of 9 minus x squared. And on the top up here, this top curve is going to be the positive version of that. So that's just going to be the square root of 9 minus x squared. Now we're going to integrate with respect to x next. We go curve to curve, then we'll go point to point. So on the left here, that's going to be negative 3. On the right here, that's going to be 3. These values here in the x direction. So we've got negative 3 as our lower bound and positive 3 on our upper bound going left to right. And this is going to be our Cartesian type integral. And you notice that we got the square roots in the limits here, and so this can be pretty difficult to evaluate, and that's why polar coordinates comes in, because you can see it's this circular shape indicates that polar might be a bit easier to evaluate, and certainly in this case it is. So let's go ahead and try and move this over into polar coordinates, and for that let's bring up a plot first. So similarly, we can go ahead and draw this region out here. So we'll start here. So if you recall from our last video, we know that dA is going to be r dr d theta. Of course, you have to throw that r in here because the differential is a little bit trickier in polar coordinates. So this is kind of what we're working with to start. And then the first thing we got to do is find out what this integrand and what's this function in the middle. And to do that, we know that we have xy up here as our function, but we want to convert these into polar coordinates. And so if you recall our equations from the last video, we have equations to convert x and we have equations to convert y. Our x is going to equal our cosine theta, and our y is going to equal our sine theta. So we can go ahead and plug in our cosine theta here for our x up here. And doing that, we get our cosine theta, and then we go ahead and plug our y in up here for the y up here, and that is going to be our sine theta. So this is going to be the integrand, and you notice that we've got 3 r's here, so we can simplify this a little bit. So before we find the limits, let's go ahead and simplify our integrand here, and we'll just call this r cubed. Cosine theta, sine theta. Okay. Now we're going to integrate with respect to r first. So we notice that our r is starting in the middle here, and it's going out from r equals 0 to r equals 3, and it's covering this whole region. Since it's covering that whole region, we can just say r is going from 0 to 3. And our theta is starting here at 0, and it's going all the way around to 2 pi. So we've got 0 to 2 pi. So this is pretty basic integral setup here. And it turns out it's pretty simple to evaluate this. The fact that we have this cosine theta, sine theta in here because of our integrand xy, that makes it it adds a little difficulty to the integral because you got to use u substitution. So in the next video we'll show how to do that, and we'll show what this actually equals, and we'll even show it in Calcplot3D just to analyze it a little bit more. But what we've shown here is the basic process for how to set up this integral, which is arguably the most important part. So hope that helps. Stay tuned if you want to see how to sort of finish this out. But until then, take care.